Let's look at a second example. This example now involves two particles, A and B, right? And they're dependent on each other. Okay? So they're attached to each other by this single cord. Okay? And there's three pulleys. The mass of A and B are given, and they start from rest. Okay? So now A will start to slide down, and you're asked to find the velocity and tension in the road, okay, of A after A has traveled 0.5 meters, okay, down, and the slope is 30 degrees angle. Okay, in this problem, realize that you are asked to find velocity again. So, the work energy method might be more convenient. Okay? So, let's again follow the procedure. Okay? Step 1, choose coordinate system. In this case, both particles, A and B, travels along this slope right here. So, I'm going to choose this as my coordinate. Okay, just a single, it's called X direction. Okay, positive point down. And then the next step is, well, you draw a free-body diagram, right, for each particle. Now, if you draw a free-body diagram for each particle, it means that you're going to apply the work energy method for each particle. Okay, let's do that. Okay, so for each particle. Okay, so particle A and particle B, consider them separately. So particle A at this position, right, I have weight going down, and I have normal force pointing perpendicular into the surface this way, and I have this tension, right, tension force going this way. Particle B, I also have weight, weight of B, weight of A. I have normal force, okay, normal force of B, okay. Now particle B now, because of the way this cord is attached, okay, I have 1 times tension, 2 times tension, and 3 times tension. 1, 2, 3. So 3T. Okay, so whatever this T is, it's 3 times that acting on particle B. So here, if you look at this right here, if you consider them separately, right? How many unknowns do you end up with? You have tension as the unknown. Okay. And what else? Well, if you apply the work energy equation, you're going to end up with velocity, okay, VA, and then VB as the unknown. Okay. And then we have this distance travel, right? So I'm going to call this delta XA. Okay. So when X travel, okay, or when A has traveled 0.5 meters, B will travel a certain amount, right? There are X speed, which is another unknown. Okay. So you have a lot of unknowns going on here. Okay. And looking at this right here, this whole picture, right? If all these unknowns appearing here, and you apply the work energy equation, okay, for each particle, right, and you have to bring in maybe kinematics, right, and you solve all these unknowns, and that's fine, but it's a little bit computational and intensive. Okay? Maybe there's a better way to do this. Now, instead of considering each particle separately, can we maybe consider both particles together? So both particles, both A and B together. So that means that this is my A, right? And then this is my B. Okay, so this becomes one single particle. Okay, you can think of it this way, right? One particle. And then the only force that appears here would be WA, alright? And then this is WB, and then you have normal force and normal force, and that's it. This tension right here inside this row doesn't appear at all in this free body diagram, because this whole thing being our system, being our particle, tension now becomes internal force. Okay? T disappears. Okay? T disappears from this picture right here. So we're not concerned with T now. It doesn't matter. Okay? So maybe it's a little more convenient if we choose both A and B as the system. Alright? So now let's apply the work energy equation. Okay? Change kinetic energy equals work going from position 1 to position 2. So change kinetic energy is KE final minus KE initial. Alright, so this is initial position, this is final position, equals work, which is force vector dotted with dF vector. Okay, now left hand side, again, let's expand it. KE is 1/2 mv squared, or v2 squared, minus 1/2 mv1 squared. Okay. And this change kinetic energy term, okay, is the total, the sum of the system. Okay, and my system now consists of particles A and B together. Okay, so you have to take into account both particles here. So this is the change kinetic energy, right, of particle A plus change kinetic energy mv2 squared minus 1/2 mv1 squared for particle B. You sum them up, okay? Total. Right hand side equals force. Keep in mind, this is the only forces that do work. Okay? In this case, it's my weight vector. Okay? Dotted with dF vector. Okay? So I'm going to keep it as this. Okay. Let's simplify the terms here. Kinetic energy initially is at rest. So this is 0, this is 0. So it's nice. What's left is 1/2 mv2 squared, right, for A, plus 1/2 mv2 squared of B. Okay? Equals, this is the sum, okay, of weight dot ds. Now, weight vector comes down. Now this is dot product, so the ds, the change of distance, okay, is the vertical component of the change of distance, okay, which is this right here. Okay, so this is delta V.